Welcome to the fifth part of oscillations, and in this part you will learn about acceleration in simple harmonic motion, force law, and energy in simple harmonic motion. The acceleration of simple harmonic motion. Again, differentiate the velocity function with respect to time to get the acceleration function. And on differentiating it, you will get minus omega square xm cos omega t plus phi. And we are back to a cosine function but with a minus sign out front. And this acceleration varies between +1 to -1, and the variation in the amplitude of acceleration is set up by acceleration amplitude am, which is the product of omega square xm. The figure C represents for a phase constant phi equals to 0, consistent with figure A and B. And the acceleration magnitude is 0 when cosine is 0, which is when the particle is at x is equals to 0. And it is maximum when cosine magnitude is maximum, which is when the particle is at extreme positions. On comparing the equations of displacement and acceleration, you got acceleration is equals to minus omega square displacement relation. In the nutshell, you can say that the acceleration A is proportional to the displacement x but opposite in sign, and the two quantities are related by the square of the angular frequency omega. A particle executing a uniform circular motion is subjected to a radial acceleration A directed towards the center. As shown in figure, such a radial acceleration A of the reference particle P executing uniform circular motion, the magnitude of this radial acceleration is omega square A. Its projection on x-axis at any time will be given by minus omega square A cos omega t plus phi, or in terms of displacement relation, you can say it is minus omega square x, a function of t. It shows that in simple harmonic motion, the acceleration is proportional to the displacement and is always directed towards the mean position. Force law for simple harmonic motion. Newton's second law of motion relates the force acting on a system, and the corresponding acceleration is F is equals to ma. By putting the value of A as minus omega square x, a function of t, you can say that the force F as a function of t is minus k x, a function of t. Here the value of k is equals to m omega square, or you can say omega is equals to k by m under the root. This equation gives the force acting on the particle. It is proportional to the displacement and directed in an opposite direction. Therefore, it is a restoring force. The force law expressed by equation 1 can be taken as an alternative definition of simple harmonic motion. It states that the simple harmonic motion is the motion executed by a particle subject to a force which is proportional to the displacement of the particle and is directed towards the mean position. Energy in simple harmonic motion. A particle executing simple harmonic motion has kinetic and potential energies both, varying between the limits 0 and maximum. The kinetic energy, you know, it is mathematically half mv square. By putting the value of V as omega A sine omega t and on squaring it, and by putting the value of m omega square as k, you will get kinetic energy as half k A square sine square omega t plus phi. And it is also a periodic function of time, being zero when the displacement is maximum and maximum when the particle is at mean position. The spring force F is equals to minus kx is a conservative force with associated potential energy equals to half kx square as derived in work, energy and power chapter. Hence, the potential energy of a particle executing simple harmonic motion is half kx square. By putting the value of x as a cos omega t and on squaring it, you will get the potential energy of a particle. From equations 1 and 2, the total energy E of the system will be potential energy plus kinetic energy, and by putting the values of both, and by taking half k a square common, you will get E is equals to half k a square into cos square omega t plus phi plus sin square omega t plus phi. And the value in the bracket, it is 1. So the total energy will be half k a square. Thus the total mechanical energy of a harmonic oscillator is independent of time as expected for motion under any conservative forces. The time and displacement dependence of potential and kinetic energies of a linear simple harmonic oscillator are shown here. And it is observed that in a linear harmonic oscillator, all energies are positive and peak twice during every period. For x is equals to 0, the energy is all kinetic, and for x is equals to plus minus a, it is all potential. And in between these extreme positions, the potential energy increases at the expense of kinetic energy. This behavior of a linear harmonic oscillator suggests that it possesses an element of springiness and an element of inertia. The former stores its potential energy and the latter stores its kinetic energy.